Lesson 4.6 is what is referred to as L'Hopital's rule. Okay, you go up to somebody that knows calculus and you say L'Hospital's rule. They might laugh at you. Just saying. Okay, so officially it's pronounced L'Hopital's rule. You will also say, do they have it in here? It's named after a calc guy. I mean, is what it comes down. I can't remember the name, but because you will also sometimes see when we talk about L'Hopital, the other way I've sometimes seen it written is L apostrophe. I'm trying to remember. Like that without the S, but I believe there's a little hat over the A. I don't know what that accent symbol is called, but looks like, But, so, anyways, looks like L'Hospital's, but L'Hopital's rule. Okay. What is today, by the way? The 15th? Okay. L'Hopital's rule is a great tool for finding limits that are often difficult to evaluate. We did limits back in Unit 1. Okay. This is the one limit tool we didn't learn at the time because this requires derivatives. We didn't know how to do derivatives. That's why this gets thrown in. So, I haven't done any limit standards since Unit 1, and then all of a sudden I had to write a limit standard up there. Okay, so it's because this is based on limits. So it can also help with determining limits at infinity for asymptotic behavior. We will use it for curve sketching in the next section as well. So here's where, when evaluating limits by direct substitution. So I don't know what you guys remember about limits right off the top of your head right now, okay? But our first go-to method was when you take the limit as x approaches 4, we would try and take 4 and plug it into whatever that equation was. Okay? Now, that didn't always work. Sometimes we got forms that didn't work. So, the types of forms that didn't work are what we call indeterminate forms. The most common ones were 0 over 0 and infinity over infinity. When we got those forms, we had to back up and try another method. Now, when direct substitution failed, maybe it was we needed to factor and something could cancel. Maybe we could write it in a different form. There were ways to get around it on the types of problems we looked at then. But there's some types of problems we didn't look at where L'Hopital's rule would help us get around it, okay? So, 0 over 0, infinity over infinity are your most common ones. You'll also see 0 times infinity, 1 to the power of infinity, 0 to 0, infinity minus infinity, and infinity to the 0. Okay, so as I said, 0 over 0, infinity over infinity, those are going to be your most common ones. Consider the limit of a quotient, so the limit as x approaches c of f of x over g of x, so where you might get a 0 over 0 or infinity over infinity. L'Hopital's rule states that when f of x over g of x has an indeterminate form of 0 over 0 or infinity over infinity at the point x equals c, then we can replace f of x over g of x by the quotient of the derivatives. So f prime of x over g prime of x. It's not the quotient rule. Okay? It's just doing the derivative of the top and the derivative of the bottom. And then we get to retry the limit and hope it works. So, L'Hopital's rule. Assume f of x and g of x are differentiable, which means you can take the derivative, on an open interval a to b containing the value c. Also assume that the derivative does not equal 0 in the denominator for all x in this interval, except possibly c itself. Then, if the limit of f equals 0 and the limit of g equals 0, that would be a 0 over 0 form, then you can do the derivatives. If the limit on the right exists or is infinite, positive infinity or negative infinity, this conclusion also holds. That's where infinity over infinity. And we can do the same thing. Couple of words of caution, because it's really good. I really need to jump into examples to make it make sense. I know, okay? In order to be able to use L'Hopital's rule, it's important to note these conditions are met. the denominator at that value, the derivative of the denominator at that value cannot equal 0. If the denominator is 0, then the limit is undefined. No oscillating functions. As x approaches c, the limit must approach a single y value. And the limit as x approaches c of f over g cannot equal plus or minus infinity. Okay? So, the side note here, and this is important if you would have a L'Hopital's rule pop up in a free response problem. In all honesty, most of the time you're going to see them in multiple choice. And they don't grade your work for multiple choice, okay? But communication in mathematics is an important skill. So proper notation and protocol for using L'Hopital's rule correctly on the exams. We're going to keep that in mind, okay? Because you have to state certain specific things in order for it to count. Okay. So in order to use L'Hopital's rule on the AP Calc exam, students should show proper procedural steps and notation. Be sure to explicitly show that the limit of the numerator is either 0, infinity, or negative infinity. So you have to, we'll talk about it, state that the limit of the numerator is 0. Same thing for the denominator, that's step 2. Step 3, you may want to state that the limit is indeterminate, as in such 0 over 0, infinity over infinity. And then you usually say or denote somehow by L'Hopital's rule, and you show that the limit there, okay? And then find the limit using proper notation. So that would be things that whenever you're taking a limit, you always write limit out front. You don't drop that off and put it back in later, okay? Okay, example 1. Jump into the basics here. You see the limit as x approaches 5 of this function. What's the first thing we're probably going to check? Plug in, yes? If I plug in 5, on the bottom, 5 minus 5 is 0. Okay, that's not a no-go yet. Check the numerator. 5 squared is 25, times 2 is 50, minus 45, minus 5.
0.
That's 0 over 0, isn't it? Okay, and, excuse me, this isn't official form, but this is kind of what my brain's thinking. My brain's thinking, oh, I got 0 over 0. So back in Unit 1, we had to have another plan. We had to check and see, oh, did maybe this factor? Did maybe that numerator factor so we could cancel an x minus 5? Okay, and if that doesn't work, I don't know, we're limited on options if we don't know L'Hopital's. Okay, and I'm not saying these other options won't still work, but we're trying to demonstrate L'Hopital's here. And so, in order to be able to apply L'Hopital's, I'm going to go very formal here. Step 1, we're going to state, basically going to do these steps 1 and 2 here, that the limit of the numerator is 0 and the limit of the denominator is 0. So I'm going to write the limit as x approaches 5, and just of the numerator, 2x squared minus 9x minus 5. What? Oh. Don't must not loud, not very loud.
Oh, sorry.
You're fine. I'm hearing, Miss Sargent, there's someone at the door.
I didn't even hear him knock.
See, okay, thank you. I'm not alone then, because I didn't hear him knock either. But then again, there's also the times when I'm looking over the door like, wait, did someone knock? Am I hearing things? You know, that happens too. Okay, you're in here for this, aren't you?
Yes.
There we go. There's that. I remember. No. Pre-calc, we didn't have a formula sheet. Okay. Which class am I in? What are we doing? Okay. Limit of the numerator equals 0, yes? Also, what about the denominator? Did we also get 0 then? The limit as x approaches 5 of x minus 5 equals 0. Okay? Officially, we need to state that. And I just looked at my notes. I officially should have parentheses around each of those, indicating it's the limit of those amounts. Okay. That's kind of steps 1 and 2 together there. Next thing. we're getting 0 over 0 here, right? And so the next piece, it says you may want to state the limit is indeterminate form. So I just, for right now, have written it as indeterminate form by L'Hopital's. Okay. And I'm not against you even saying 0 over 0. So now, my numbers are kind of off. I should have labeled that. Is that going to throw you guys off? I should have labeled this as officially 1, 2, 3, 4. Well, 5 is just fine, proper. Okay. Sorry, I'm arguing with myself. Okay. Step 3. We're officially going to do L'Hopital's rule, which means, okay, what's my original limit? I'm going to write my original limit. The limit as x approaches 5 of 2x squared minus 9x minus 5 all over x minus 5 is going to be equal to, so that's this right here. And what's it going to be equal to? What can we do with both top and bottom? We can take the derivative, not a quotient rule. Okay, this is something special. This is L'Hopital's rule, derivative of the top, derivative of the bottom. So it's still going to be the same limit. The limit as x approaches 5 of, what's the derivative of 2x squared minus 9x minus 5?
4x.
Over, what's the derivative of x minus 5? 1. Now, your last step is to actually do that limit. Okay, yeah, plug it in, which, so here, if I do the limit as x approaches 5 of basically what? It's 4x minus 9. What are you getting?
0. Wait, no.
4 times 5 is not 9, right?
Yeah.
We get what? 11. Okay. It happens. It happens a lot more than we want to admit, right? We have that moment where 4 times 5 all of a sudden becomes 9. There's no answer. It's just a moment.
It's close.
You know. Okay. That's officially L'Hopital's rule.
So all
Okay.
we do is take the derivative of it.
The short of it is you take the derivative of the top, the derivative of the bottom, and you retry the limit. That's the short of it. Now, one thing I want to show you, okay? I said that L'Hopital's is not necessarily the only way to do this. This is an example we could have done back in Unit 1. Because 2x squared minus 9x minus 5 would factor. And so, I don't know, I know you guys aren't huge about my whole just guess and check, but 2x squared has to break into what? 2x times x, right? What's 5 have to break into? 5 and 1, right? Those are my only options. Now, I can see what's going on here, so I'm going to say 5 and 1. If it multiplies to be a negative 5, I need a positive and a negative, yes? Somehow I need my middle terms to give me negative 9, so it'd be what? 2x times 5 needs to be negative 10x. 1x times x needs to be plus 1x. And what happens here? Your x minus 5 can cancel. What happens if you plug 5 into 2x plus 1?
11.
You get 11, yes? Okay, so could we have done this one back in Unit 1? This is an easier version. This is one, you don't have to use L'Hopital's because it could factor. Okay? However, is that always the case? Definitely not. For example, number 2.
Oh.
Now, this isn't a factoring option. I would probably I would say back in Unit 1, we probably would have tried this one by multiplying by the conjugate of the numerator, if I had to guess. I don't know, but that's not what we're going to do today. We're going to look at L'Hopital's. Now, first of all, do a quick plug-in. What are we getting? Because you can't use L'Hopital's unless you get an indeterminate form. 4 minus negative 5. 9, square root of 9 is 3, 3 minus 3 is 0, over 0. Are we going to get 0 over 0? You are, okay? And again, not that this is official, but my brain kind of like, okay, I need to think that. So officially, for official notation, separate your numerator and denominator. The limit as x approaches negative 5 of the square root of 4 minus x minus 3 equals 0.
Do we always have to do the proper notation?
Not necessarily. We're going to practice it some now because I need to kind of train you that this is proper notation. As I said, if you see this in multiple choice, do you have to show proper notation in your work on multiple choice? No. Okay? But if you see this in a free response, somewhere in there, you need to state why it is we're allowed to use L'Hopital's rule. Okay, and what I kind of even did on this one is, okay, we get 0 over 0. And so I even kind of did this one differently. I then said, okay, indeterminate, see, I can't spell today. Indeterminate by L'Hopital's, okay? So the limit as x approaches negative 5 of originally it was the square root of 4 minus x minus 3 over x plus 5. The limit as x approaches negative 5. What are we doing here? Derivative. Can I get the easy one out of the way? What's the derivative of the denominator? 1. Derivative of the numerator.
1/2 4 minus x. No.
Keep going.
1/2 4 minus x minus 1 times 1.
I need a power.
Negative 1.
I hadn't even, when I said I need more, like I was expecting you to go on, I hadn't even paid attention to the fact that we were going to have a chain rule there. My brain wasn't to that part yet. Okay, my brain was, hey, I need the power. Are you with me on what I just did here?
Well,
It was 4 minus x to the power of 1/2. So you multiply by 1/2 out front, keep the 4 minus x, subtract 1 from 1/2, puts me at negative 1/2,
take the derivative.
times the derivative of 4 minus x, which is negative 1. So if I wanted to clean this up, I don't know that I'd plug in right there. You could. Why did I underline limit there? Gosh. Limit as x approaches negative 5. This is where I want my fraction bar. What about the 1/2? Well, it could if you want to leave a fraction within the problem, or the 2 can go in the denominator, yes? What about 4 minus x to the negative 1/2? Bring it down, and it's really square root of 4 minus x. Negative 1. Well, this is a 1. Somewhere there's a negative, yes? I don't really care where you put the negative, but a lot of people would put it out in front of the fraction bar. Now, have you tried it? Does it work this time? Well, okay, here's the deal. I'm not getting an indeterminate form, because on top, what am I getting? Negative 1. So it's not, I know I'm not getting anything bad. Yep. Okay. Okay. Getting the basics, yes?
That's not too bad.
It's not. I love L'Hopital's.
Oh,
I love L'Hopital's. Why are these boxes so big? Not because the problem is that hard.
Because you gotta write out.
Because we're showing the proper form. That, to be honest, if I was just doing some of these, like this next one, just me, just trying to get an answer to the problem for maybe multiple choice or something, I'm not going to necessarily show all my steps. Okay? Okay. That's fun, though, with L'Hopital's. Okay. 3. As x approaches negative infinity. So what happens on top, negative infinity, when you square it?
negative infinity. Positive infinity.
Negative infinity times negative infinity really is, my brain thinks positive infinity, yes? E to the negative of negative infinity. Well, that's going to be e to the positive infinity, yes?
So
What's e raised to a ginormous power?
positive.
It's going to be a positive infinity. It's going to be getting bigger and bigger and bigger. So again, we are of the form, an indeterminate form. This time it's the infinity over infinity. Okay? So 0 over 0, infinity over infinity, or negative infinity over negative infinity. Those are your most common ones. Okay? So, officially, okay, don't take up the whole box, FYI. The limit as x approaches negative infinity of x squared is equal to infinity. The limit as x approaches negative infinity of e to the negative x is equal to infinity. And so what is that? That is a indeterminate form, right? Indeterminate form by L'Hopital's. So what are we going to do? The limit as x approaches negative infinity of x squared over e to the negative x. I just rewrote my original limit. And it's going to be what? The limit as x approaches negative infinity of, not quotient rule, just
Oh yeah.
drew the top, drew the numerator, because we're doing L'Hopital's rule.
2x over.
Times negative.
So negative e to negative.
I'm going to write it as negative e to the negative x. Okay? Okay, let's plug in. 2 times negative infinity.
Negative.
A negative infinity. Okay? Denominator. Negative of e to the negative of negative infinity.
Negative infinity.
Yeah, because it becomes e to the positive infinity again, but it's negative that. Negative infinity. What just happened? Still in determinate form. Guess what we get to do?
Take the infinity again.
What?
You get to do L'Hopital's again. L'Hopital, you can keep looping through L'Hopital's as many times as you need
So
to
can you just keep doing it until it gets easy?
until it becomes doable.
What?
Which is why I said leave room. So, we're going to do round 2 essentially. So, the limit as x approaches negative infinity of 2x is equal to negative infinity. That was my numerator. The limit as x approaches negative infinity of negative e to the negative x is equal to negative infinity. Again, I'm teaching it, okay, guys? You have to. I'm not a fan of writing all the fluff out either. I'm really not. But I need you to know how to do it if it comes up on AP. Fair enough?
Yeah.
And if I don't teach it now, when am I going to teach it? So, here again, negative infinity over negative infinity, we have another indeterminate form. So we're going to use L'Hopital's. Okay, so this time, the limit as x approaches negative infinity. Where are we at? We are at 2x over negative e to the negative x, yes?
Yes.
Okay, what do you got?
2 over e to the negative x.
The limit as x approaches negative infinity. Derivative of 2x is 2. That's always a good sign when your x disappears. That means we're not going to L'Hopital again.
Oh, yeah.
Derivative of negative e to negative x is basically negative e to negative x times another negative, which is going to make it positive e to the negative x.
Do we have to do like another negative?
Huh?
Do we-
I did do another negative 1, but that multiplied by my negative out front. Right? So negative times negative makes it positive. Okay, so if I plug in, I got 2 on top. 2 is 2.
True.
E to the negative of negative infinity. Infinity.
I hate infinity.
This should be like,
Okay, now, so this is, okay, remember we talked about this. This is taking 2 and dividing it by a very, very large number, yes? There's my non-calc, there's your non-calc reminder. It's 2 divided by a larger and larger and larger number. So, 2 divided by 100 is, no, 2 divided by 100 is
0.02.
2 100, so 0.02, right? 2 divided by a million, point zeros, however many zeros, 2. Are you seeing where I'm going with this?
Yeah.
What's my number? What's that result going towards? Smaller and smaller and smaller, approaching 0. Okay. It's the idea of limit behavior, guys. And I know when we did limits back in Unit 1, we talked about the whole idea of dividing by infinity. It's been a couple of months, okay? So anytime basically you have a constant on top and you're dividing by a number getting bigger and bigger and bigger, the bigger denominator gets, the smaller that fraction value gets, the closer it becomes to 0. So anytime you're dividing by infinity, constant divided by infinity, shortcut is it's 0.
But we can still do it, right?
What do you mean?
Like, even though we got,
We're done. We didn't get an indeterminate form of 0 over 0 or infinity over infinity. As soon as we got just a 2 on top, I know I'm done. This is the last round. It's just a matter of, you can still get infinity as part of your answer. You just can't have on top of it something. Okay? Okay. Example 4. Guess what happens if you add negative 2 on top and bottom?
Yeah.
You get 0 over 0. Good guess. Okay. Now, you can write out these functions each time. Or, this is a calc thing that, okay, what do you want to call the top? Let's name the top f of x.
Right.
So I have to write it out that this is x cubed plus x squared minus 8x minus 12. I'm going to name the denominator g of x. Because I have named those, I don't have to keep writing those equations out every time if I don't want to. I can refer to them within my work as f and g. Fair enough? That is allowed. That is an option. Okay, now, to get my official notation, the limit as x approaches negative 2 of f of x, I didn't make you do the math, but Tate's luckily guessed 0, right? And the limit as x approaches negative 2 of g of x, we also guessed to be 0. Okay? So, and here's how I kind of shortened up my notation. We're going to do the limit as x approaches negative 2 of f of x over g of x, right? And I stated each of my limits, right? I stated them as each 0. I'm going to kind of shortcut right here and say by L'Hopital. Okay? I'm kind of shortcutting right there. But I can do that. And now what are we going to do? We're going to take the derivative. Now, we're going to have to write out the derivative so we can see what's going on. Derivative of f.
3x plus 2x minus 8.
And you left off a squared there, right? 3x squared?
Yeah.
Okay. Derivative of the g of x.
3x squared plus 16x plus 12.
Okay. You want to guess what's going to happen? And if you want to throw in some 0 over 0s, just kind of as notes here, you can. Now, what is it that just became 0 over 0? What could I refer to that top as?
F prime of x.
That was f prime of x, wasn't it? Can I say that? Is that legal?
Yeah.
Yeah, that is f prime of x. So the limit of f prime of x was 0, and the limit as x approaches negative 2 of g prime of x was 0. Okay. So the limit as x approaches negative 2 of f prime of x over g prime of x. And again, we showed that they're both zeros, right? So I'm going to say by L'Hopital's, limit as x approaches negative 2, derivative of the top, dang it, 6x plus 2, derivative of the bottom, 6x plus 16. It actually works this time, folks, if you plug it in. 6 times negative 2 plus 2
Negative 10.
over 6 times negative 2 plus 16. Okay. Now, for reference, as you guys are cleaning up, you technically at this point could have stopped with your answer like that.
Well, it's the same thing.
Any of those would be okay answers.
I like that.
It's weird. That is a struggle for me.
For you or for AP?
For AP, definitely.
Maybe.
I don't know. I hesitate. I still prefer you guys to take it all the way out. But, okay. That takes us down to 3 pages for Monday.
Yep.
Thank you.